Today, today we're going to talk about electric potential energy. This is the natural progression from forces to the field, and now we're going to talk on energy. The objectives for this lesson are primarily to be able to calculate electric potential energy and another measurement that we're going to call electric potential. Okay, first off, potential energy is energy stored whenever I have two objects that are held in place temporarily. Examples of this are a book that I hold above the earth. In this case, the two objects are the book and the earth. Or in the case of a spring, okay, the elastic potential energy, as I stretch a spring, I'm storing energy in that spring, similar to a rubber band. Okay, so the two objects in this case are the spring and whatever I am stretching it with. In this case, it would be my hands. Okay, so charges are similar, okay, because I have a force between those two charges, either attractive or repulsive. Okay, and when I hold them in place, I am storing that energy. If I release one of them, it will either move towards it if it's attractive or away from it if it's repulsive. And that force, which is applied over a distance, either as I get closer or as I get farther away, that force and that distance corresponds to work, and that work converts the potential energy that I stored into kinetic energy. Like all energies, electric potential energy is going to be a scalar and has the units of joules. The formula that we use is going to be Q over R. Okay, the big Q and the little q doesn't really matter. In this case, I labeled the left and the right one Q and little q as shown here. Okay, so here's the big Q, here's the little q, but it really doesn't matter because it's commutative. Okay, one way we can think of this, and this is an oversimplification and is mathematically inappropriate because it's a calculus derivation. But one way we can think of this is that potential energy is force times distance, basically that work that I talked about before. And that work, when I multiply that force, it's KQQ over R squared, just Coulomb's law, times R. One of the R's on the bottom cancels, and I'm left with the formula for potential energy, which is KQQ over R. The actual formula is actually actual derivation is actually pretty complicated. Now, electric potential energy is a scalar, okay? So the direction doesn't matter. I could be, hold the two charges, left to right, up to down, at a diagonal. It really doesn't matter. The only thing that matters is the magnitude of the charges and the distance between them, okay? But the sign of the charges in this case does matter. Okay, so I would keep the sign here. I know for fields and force, the magnitude of the vector should always be positive, so I could ignore the sign. But for potential energy and later for potential, the sign of the charge matters. So when it is possible to have a negative potential energy, okay, when the charges are attractive, one of them is going to be positive, the other one is negative. And a positive Q, negative Q, when I multiply them, results in a negative potential energy. When the charges are repulsive, I have the same sign, two positives or two negatives. When I multiply those, I'll end up with a positive potential. Okay, and as I stretch these things, or as I move them farther apart, okay, the magnitude of that potential energy is going to decrease. Okay? Looking at graphs for the potential energy, on the left side we have the potential energy associated with repulsive charges, notice that it's positive, and attractive charges on the right hand side. The formula is given on the bottom, and this is the graph of a function that's 1 over r. It's a hyperbola in mathematical terms. I'm not going to ask you what the shape of this curve is because that really belongs in math class, but it's very useful to know. Okay, notice as I move farther away, okay, as I move farther away, my R increases, okay, whoops, the magnitude decreases, or you could say it approaches zero, whether it's positively or negatively. So here's an example of a problem, okay, I have two charges, I put them on the number line just so I have a distance between them. I could simply tell you the distance, but I just put them on a number line. So I have a 5 millicoulomb charge and a 2.5 millicoulomb charge, separated by 11 meters in this case. To calculate the potential energy, I just plug it into the formula, which is KQQ over R. Okay, so in this case, when you plug all the numbers into your calculator, you find that it's 1.02 times 10 to the 4th joules. Okay, that's 10,200 joules, a fairly large amount of energy. And if I was to say release Q2, that energy would be translated into kinetic energy as Q2 moves faster and faster going away from Q1. The other term we're going to be working with is electric potential. Just like when we analyzed electric force, we looked at the force between two charges. And then we moved to the electric field where we looked at what happens if I only have one charge. Okay, this charge generates an electric field. It's a similar concept for electric potential. Electric potential energy requires me to have two charges. Electric potential, or another term we will use, they're nearly synonymous, is voltage. Okay, electric potential is going to be associated with a single charge. Okay, so electric potential and voltage, like I said, are synonymous. Another term we'll run across later, but not right now, is voltage differential, and that would require me to have two different points in space. But electric potential is measured at a point in space, just like we measured the electric field at a point in space. Okay, and so there would be a central charge, capital Q, and a distance from that point in space to the charge, and that would be R. And we could calculate that electric potential using the formula KQ over R. Again, the sign of the charge is going to be important. You can have a negative voltage if the central charge, the capital Q, was negative. Okay, and by definition, when my distance goes out to infinity, I'm so far away from this central charge that I don't even know it exists really. And my voltage or electric potential at infinity is by definition or by convention is going to be 0 volts. Okay, and electric potential energy would also therefore be 0 joules at infinity. Okay, so electric potential is a way to think of it as if I took a small positive charge and I placed it at that point in space, what would the potential energy be at that point? Okay, and so the electric potential energy at that point, another way to think of it is, is that my potential would be the potential energy per unit charge, Q. Okay, so that's what I mean. Okay, I could take a small point charge and put it there, okay, and measure what the potential energy would be at that spot. Okay. Although I wouldn't really test you or ask you to calculate potential energy for multiple charges, I could ask you to calculate potential for multiple charges at a point in space. Okay, so because it's a scalar, direction doesn't matter. Distance does, direction no. And so the electric potential at a point in space is going to be the sum of the electric potentials from all the charges. Let's look at an example of that. Okay, I have 4 charges of magnitude 1.5 microcoulombs placed around a 3-meter radius circle. Okay, and I asked you to calculate the electric potential at the center of the sphere. Well, since my radius is 3 and it's a circle, the distance for all of them is going to be the same. It's 3 meters. Okay, and the potential from one of them, okay, is going to be the same as the potential from all of them, each one of them. Okay, so I have the potential from one is KQ over R, or 9 times 10 to the 9th times that 1.5 microcoulombs, which is 1.5 times 10 to the minus 6, divided by 3 meters. Okay, and to find the net, okay, to find the net one, all I have to do is take this and multiply it by 4. Okay, because I don't really need all of them. Okay. And if I do that, I'll find that I end up with a value of, why does that keep popping up? Okay, 3, 4.5, 16, 18 times 10 to the third volts. Not sure why that keeps popping up. Okay. So that's how we would do it for multiple charges. Could calculate each one individually, or if their distances are all the same, then it really doesn't matter. I can just multiply or add them all up prior to sticking it into my formula. Okay. So just to summarize, the difference between the electric force and field versus electric potential energy and electric potential. Remember, you're going to need to read very closely and make sure you know what I am asking you for, okay? The words are very close and very similar. Okay, the two F words, force and field, those are the vectors, okay? They point somewhere. Direction matters, okay? Because they're vectors, they should always be positive. The magnitude of your vector is always positive. The direction is what determines whether you add or subtract. Electric force is going to be in newtons. Electric field is in newtons per coulomb. Both of the F1s are going to be inversely proportional to r squared. Either KQ over r squared or KQ over r squared. Okay. Similarly, okay, on the electric potential side, these are all scalars. The P words are scalars. They can be negative, and direction doesn't matter. Distance will, okay, distance between the two charges or distance to a central charge. Okay, these are going to, potential energy is measured in joules, and potential is measured in joules per coulomb, or another, the term we'll use more likely, is volts. And these two are going to be inversely proportional to R. Okay, so in this case it's K, stop it, Q over, I don't understand, over R, go up there, or KQQ or KQ over R. Okay, so those are our four formulas that we will be working with towards the end of this unit. Okay, thank you.